Hi, my name is Alyssa MacMeekin. This is my 5th year at Key School, my 12th year teaching overall. I teach the junior level science, integrated science course, as well as advanced biology for the seniors.
And my name is Lee Zanger, and this is my 11th year here at Key, and I teach the sophomore course, and I'm head of the science department. And Tom, if you can go to that first slide, please. A few years ago, some of my colleagues and I, it was just before Alyssa got here, sat down and over a series of summers, developed a completely new science curriculum. And what we did is, rather than have the traditional divisions of physics, chemistry, and biology, we designed 3 courses that are fully integrated, that have components of each of those disciplines in each of the years. Each of the courses is focused on a particular theme. And then by senior year, the students are prepared for our advanced electives. Our biology, physics, and chemistry courses all prepare kids, if they're interested in taking the AP exam. It prepares them for those tests. And then we also have sort of alternate between oceanography and astronomy as some other options for seniors. The reason we took this task on is we realized that the traditional disciplines of science are completely artificial. And if you actually look at the Nobel Prize winners over the last few years, every single one of them is interdisciplinary. It's usually a biochemistry thing or a chemistry physics thing, or those divisions are just not real. The other thing that we realized is that a lot of times when you're teaching science, you're teaching these kind of esoteric, very abstract concepts. And, you know, for us science teachers, they're fascinating. We're like, oh, that's so cool. And the kids are kind of like, not so much. But what we are able to do is teach those concepts and then immediately show how they are applied. Alyssa's going to talk about an example of that. And as we go through the curriculum, I'll mention a few of them as well. But you know, information from one of those traditional disciplines often is applied in a really creative and interesting way in another discipline. And our curriculum now allows us to explore those directly and bring a relevance to these ideas that it might not otherwise have. The other thing that I want to mention about this is I taught chemistry for a really long time. And in chemistry, there are I taught it to sophomores, right? So there are some topics that were frankly really easy for sophomores. And there were other topics that really were too complex and abstract for sophomores, at least for the general kind of average, kid. And so what we've been able to do is position the topics in grade levels that are appropriate for the majority of kids, so that they are confronted with appropriate challenge and interesting ideas, but not, at least not usually too overwhelmed by what they're doing. And then the last piece is because we're not so tied to these very traditional curriculums, we have a little bit more time for some of those engineering and experimental design type projects throughout our curriculum. So details. The freshman year course is integrated science data, sophomore year is energy, and then the junior year is our systems course. Let me just give you a little bit of detail about those courses so you have a sense. And Tom, you can go to the next slide. Our data course starts with study of the scientific method, looking at observation, inference, analyzing data. How do we take the numbers that we've collected and put those into some meaningful model that will express what we've seen and hopefully predict other things in a similar situation. And if you look at that list of topics, you'll realize that each of them is one that students can easily gather data on. They'll walk past our electronic sensors to do the laws of motion, and we have little plungers that they've compressed for gas laws, and they grow plants and analyze the phenotypes as they look at genetics. And through those various units, the students sort of rediscover those laws. Yes, we all know Boyle's law of gas laws, but our students rediscover them. And it's important that I mention that, because very rarely in our curriculum do we say, here's whatever fact. Rather, we're trying to lead the students through a series of experiments, discussions, debates, to come to understand these deeper levels. And then often we'll give them the vocabulary. It's, oh, you know what? We already actually know this, and it's called whatever law. Let's see. Tom, can we go to the next slide, please? In our energy course, we take that idea of experimentation and understanding, and we look at energy. We look at that through laws of kinetic energy and gravitational potential energy, and the kids, again, are gathering data, developing ideas, coming to understand those concepts and how the law of conservation of energy is seen in those ideas. Again, law of conservation of energy can be seen as we look at electrical circuits. And one of the questions in electrical circuits is, okay, well, so we have these circuits and we keep talking about electrical potential, but where does that come from? Well, the answer, at least in many cases, is it comes from electronic structure and atomic structure. And so we look at that, and that's sort of a traditional chemistry topic, obviously. But again, we've given it a context, we sort of have this broader question that we're raising and then trying to answer through that study of some very, very abstract things. Once you understand electron structure, you know that some things get more stable when we lose or gain electrons, and those are called oxidation reduction reactions. And the year culminates with a study of cellular respiration, which is in fact a profoundly important redox reaction. Again, so we've brought together all of these different ideas, and we think that we have given the kids a background to understand cellular respiration at a very, very sophisticated level. It's not just a question of memorizing a bunch of ideas, it's seeing a recurrent theme about energy throughout the year. And from there, I'm going to turn it over to Alyssa, and she's going to talk about the course she teaches, and then she'll lead us through a little bit about our more general philosophy.
Thanks, Lee. So as I say, I teach the junior level class, which is integrated science systems. And I just want to say the integrated science curriculum is part of the reason that I came to Key. When I interviewed with Lee for we had the initial phone call, he told me about it. And that's when I, as a science teacher, knew that that's why I wanted to be at Key. So it's a pretty big deal that we do this. So once they get to their junior year, we look at systems, and we look at systems through the idea of a system. What does it mean to be balanced or at equilibrium? What does it mean to apply stress, and how does it respond? So we start with simple harmonic motion. They build pendulums, they play with springs, and we sort of look at that, and that sets the tone and gives them a visual for our whole class. So then we get into, right now we're doing ecology, and that feeds us nicely into evolution. But the unit that really, I think, it's my favorite unit, and it really just defines everything that we try to do with integrated science, is looking at our DNA and protein synthesis feeding in from bonding and intermolecular forces. Tom, will you give me the next slide, please? So what we do is we start with molecules, bonding, intermolecular forces, and we understand how things interact on a microscopic level. And then from there, we build into complicated molecules. We start building proteins and DNA, and now we can look at why they're shaped the way they are, which leads us to how are they built into that structure, and how does that give us any idea of their function, right? Proteins function almost entirely based on their shape. And so if we know how those carbons are linked, how those hydrogens are linked, and why they're shaped the way they are, then it gives us a better idea of why they're going to function the way they are and how they function. So it's really, it's been wonderful to teach in context. I'm a biologist by trade and by degree, but really everything is just interconnected, and being able to teach our kids that, they really get a good foundation of understanding the interconnectedness of things and how to think about science, right? You don't think about science as, well, this is just biology and this is just chemistry. So it helps them look at the big picture and the larger concepts that really unite the whole scientific community. Will you go to the next slide, please, Tom? So as a department, our goals are pretty, they're pretty directly related to this integrated science. We want them using data, developing models, understanding how these how the data supports or doesn't support hypotheses. And
Looks like Alyssa's having a little trouble with her audio. So let me just kind of pick up here.
discovery.
You're back.
Am I? Oh, I'm so sorry. I froze. Oh dear.
That's okay. Go ahead.
Okay. So, so we really focus on analyzing error. We focus on discovering what is happening as a group through discussion, through models. And we really focus on problem solving and looking at this big picture collaboratively as to how everything fits together and how to move through a lack of understanding into building knowledge and really complex concepts. So it's, as I say, I am very privileged to be able to teach in the way that we do, and being at Key School, allowing me to do that is phenomenal.